says it's both a genetic engineering thing and it's a sort of people try to do estimates of how much of your population variation you use up when you try to select for something. But most of them are not selectable with the current understanding. We assumed that everything reproduces exactly as its fitness level says. That's also not true. There's a large amount of randomness or noise. Right? You get whatever genetic makeup. A terrible thing might happen. You might walk down the road and be hit by a car. It has nothing to do with your genetics. Right? My genetic, I happen to be dyslexic. Right? You notice I'm not very good with names. Right? It doesn't affect how many kids I have. I have 5 kids. Right? It's a slightly deleterious something or another in my genome, but I still have 5 kids. Reproducing too quickly. So mutations, and what a lot of this comes down to, mutations occur at the molecular level, meaning a mutation either in a piece of your genome, a piece of sequence of DNA is moved around or transcribed wrong or misspelled or something. But selection occurs at the organism level, right? And it only occurs when this selection actually only occurs when there's a large difference between probability of reproduction, right? For humans, reproduction rates have a lot more to do with culture than they do your genetics. So it's very sort of difficult to select one out of lots. And so, last slide. So mutations in humans, just kind of reiterating what they are. So John Sanford calls this process of the buildup of bad mutations genetic entropy, right, randomness, and it accumulates like rust. And so here's the picture that John puts together. Now, he's a geneticist. I am glad to say here's a theorem. I'm glad to say Fisher's corollary is false and state my name on it as a mathematician, as a profession. Right. This is I'm going to reference John Sanford for both this analogy. He's a respected geneticist, but I'm, and as far as I can tell, it's consistent with my understanding. So here's his thing. You have a car, gets a little bit of rust, or a little mutation, it's a little deleterious. Doesn't affect how the car functions very much. You replicate the car a couple of times. Each of those replications get a little more rust that don't affect the car very much. You replicate them a bunch of times. Eventually, you have rust that builds up over years and years, the rust being the analogy of deleterious mutations. That from one generation to the next, or between the siblings of the next generation, aren't enough to distinguish between them. But over time, you have rust that's going to eventually cause a muffler to fall off, or cause things to fall apart. Now, there's a lot of subtleties that go into that, and whether that's happening, and how much junk DNA there is in the DNA plays a role in that. And so I don't want to simplify it and say, therefore I've shown that it works like that. But one of the world's greatest geneticists, that's his understanding of it. He wrote a book describing it and deriving it with all full references and everything. So anyway, so that's the end of the talk. And just I thought I'd put those back up as a last slide. So questions.
I mean, I guess my basic feeling on this. I mean, I don't think going after this Fisher's assumption of 50-50 is a fair way of going at the modern biological situation. I don't think anyone in biology would claim 50% of mutations are beneficial. I don't think that even if it's 1 in 1,000, 1 in a million, I don't think you've shown anything that seriously says that's problematic for evolution. I mean, if as one of your slides said, you have 60 to 175 new mutations per person, let's pick a nice round number in the middle of range, assume it's an average of 100 per person. Well, there's 7 billion people on the planet. That's 700,000 positive mutations every generation. By those numbers, I mean, that's plenty for evolution to work on.
So that's the question. Would that be plenty for evolution to work on? And the geneticists estimate, how much you could select. So what percentage of the population you would have to kill off. And each of those 7,000, I don't know, 700,000 has 100 other bad mutations along with the beneficial ones. So there's 99 bad for the one beneficial. So there is a discussion that goes down that route, which is what John Sanford addresses. So, but the degree to which you can select against them, the current understanding, you know, I don't have a theory of improvements of being a math guy, but the best understanding, you know, is that there's not enough to select for. But
I mean,
those things are disputed.
Yeah.
The central thing, though, that the center pin of what is in textbooks and what people use to justify the process of evolution, why mutation plus selection plus time equals all life, that central theorem is false, is a big deal. Does it tell you evolution should be thrown out? Absolutely not. But it tells you that this thing that we've held up as, hey, here's something we can hang evolution on.
Thank you.
It doesn't work. That's the point of that. Thank you. So you're right, the way science goes is, this doesn't work. Well, we either need to refine our hypothesis or throw it out or get a new one.
Yeah,
Right.
I'm just saying, I don't think anything you said really makes a serious case that something's not working with evolution to explain the history of life. And the other big point I would make is you seem to talk about fitness in some kind of absolute sense. Like we can just look at an organism or a genome and say, this one's more fit than that one, this one's less fit than that one. And that's not true. I mean, you know, to take, for example, a penguin is very fit in the particular environment of Antarctica. A penguin would be very unfit in the environment of Charlottesville. Fitness is relative to an environment. And when we're talking about the fitness of a gene, you talked about some of the complexity at the end. Yes, that environment includes the other genes in the organism, the other organisms in the species. It does get very complex to work out. But
two really good things in what you said. Fitness is equated to reproduction rate both in Fisher's work and in what people do when they do most of evolutionary stuff today, which I always find disturbing. Rats reproduce much more quickly than people. Mosquitoes reproduce much more quickly than rats. But that doesn't give you any sort of, it doesn't give you any sort of either evolutionary ranking or complexity ranking, depending on how you want to describe bioinformation, right? So that's a slightly bothersome thing that bothers me across all of evolutionary thinking. And in all of evolutionary thinking, they equate the two and they work with it. You know, that's supposed to be why things get more fit, because reproduction is more fit. But it's not. So to me, that bothers me about evolution. The other thing you mentioned is really, really important. Penguins are fit in their area. And what population geneticists do is the standard understanding of population genetics. And so John Maynard Smith wrote the culminary textbook in population genetics, or the main textbook. And in his book, he says that what they see is all population genetics assumes that you go to an equilibrium for the environment you're in, that evolution only happens when a species is geographically separated, meaning that they're separated into two groups and they can't reproduce with each other anymore. So, but of course it goes back to the fact that when they observe it, they see stuff going to equilibrium, which is consistent with this, right? So.